This is problem 76 from the electric field. A hollow metal sphere has inner radius A, outer radius B, and total charge Q. Find the electric field at all points in space and sketch the radial component of the electric field on the graph at right. We're going to start off when R is less than A, so that's inside the hollow portion of the sphere. So this radius here is A, and this radius here is B. So I want to write an expression for the surface area parallel to the electric field. Actually, I don't want to do that. I just want to say if we're inside the hollow portion, Q enclosed is equal to 0. And Gauss's law says E dot dA is equal to Q enclosed over epsilon naught. But the left-hand side has to equal 0 since Q enclosed is equal to 0, which means the electric field is equal to 0. So we'll just say that. So, because it doesn't really make sense to write an expression for the surface area parallel to the electric field when there is no electric field. So if you're inside a conductor, you know the electric field is 0, you can just say this, okay? But remember that although Gauss's law is true, it is not always useful. So if I were to draw a Gaussian surface over here, it's not enclosing any charge. And although the total flux is 0 in this case, the electric field over here is not 0. Okay, so you have to be careful when you use Gauss's law that you are applying it correctly. But inside a conductor, the electric field is always 0, so I'm safe to say this. And we do have to know something about the electric field to begin with if we're going to use Gauss's law, because I have to write an expression for the surface area parallel to the electric field. In order to do that, I need to know the direction the electric field is pointing in. In this case, I know there is no electric field, so I'll just say so rather than pretending that it is pointing in some direction and writing down the area and then figuring out that it's equal to 0. Okay, so now we want to write an expression for the surface area parallel to the electric field when we're between A and B. That would be here. Well, we have a hollow metal sphere with a charge Q. Where is that charge going to be? It's on the surface, and as we saw in previous ranking problems, if your shell is enclosing another sphere, whatever the charge is on the outside of that sphere, that would be the charge on the inner surface of the shell. But we have no charge enclosed by the shell, so there would be no charge on the inner surface here. All the extra charge is going to be on the outer surface of the sphere. So we're still not enclosing any charge because all the extra charge is on the outer surface. And if we did have a case, hang on just a minute. Okay, so if we had a case like this, which was a ranking problem that we looked at, where there was charge on the inner sphere and then charge on the hollow surface, actually I think it would be more like this one here, which was a homework problem. We saw that the charge on the inner surface of the shell is the same magnitude but the opposite sign as the charge on the surface that it is immediately enclosing. So if we're not enclosing any charge, the charge on the inner surface here would be 0, which means we're still not enclosing any charge. But if we did have charge on the surface here, when we draw our Gaussian surface here, the net charge would still be 0 because the charge on this surface is equal in magnitude but opposite in sign to the charge on this surface. So we're still inside a conductor and the electric field is still equal to 0. So Q enclosed is equal to 0 and the electric field is equal to 0. Where you would have to be careful in a case of nested conductors, so let me redraw this over here. Inside the conducting sphere, the electric field is 0. Suppose we have another shell here. Inside the shell, the electric field is equal to 0. Where you would have a non-zero electric field is here. So here if you have charge on this enclosed sphere, you would be enclosing charge. You're between two conductors, but it doesn't count as being inside a conductor. So here you're inside a conductor, not enclosing any charge, so the electric field is 0. Here you're like within a conducting shell, but you are enclosing charge, so you do have an electric field. Okay, because if you have positive charge on the surface here, you would have negative charge on the surface here, and in that case the electric field would be pointing outward like that, but it would be 0 here and 0 here. Okay, now that we've beat that to death, we'll go on to outside. And write an expression for the surface area parallel to the electric field. That, remember, is always the surface area of my Gaussian surface, which has a radius of little r. So that would be 4 pi little r squared. Q enclosed, total charge is Q. I'm enclosing all of it, so that's Q. Applying Gauss's law, I get E times A is equal to Q enclosed over epsilon naught. E is equal to Q over A is 4 pi r squared times epsilon naught. You can leave your answer like that, or you can take the 4 pi epsilon naught in the denominator and turn it into a Q in the numerator, and you can even write it as a vector if you want. This is pointing in the r hat direction, so any one of those is acceptable. You could also write it with the epsilon naught and the vector r hat. And it's 0 as we go from the center to A, it's 0 as we go from A to B, and then we pick up here at kq over r squared, and it goes to 0 as we go far away. So that is the graph for the electric field, and that concludes problem 76.